Hello everyone, it's a great pleasure to have here Maria Vincenzi today. Thanks a lot for accepting our invitation. Maria is currently Associate Professor at the Department of Physics at the University of Oxford. She was previously a NASA Einstein Fellow at Duke University and obtained her PhD at the Institute of Cosmology and Gravitation at the University of Portsmouth. Maria has been co-leading the DESS Supernova Cosmological Analysis, and she is now mainly involved in LSST DSC, where she is co-convener of the Time Domain Working Group. Today she will present the cosmological results from the Dark Energy Survey Supernova program. Maria, please, you can start when you're ready.
Okay, thank you very much for the invitation. As Eleonora just mentioned, I'll give a brief overview of the DES Supernova cosmological results. These results came out more than a year ago, but I guess they played quite an important role into all the new exciting cosmological results that came out in the last year. So I'll try to kind of give you a little bit of more details on the analysis and put this data set into context, let's say. And then at the end, I would like to talk a little bit about what supernova cosmology should look like in the next 5 to 10 years, and how it should help more and more to answer all these interesting questions about dark energy. So I know I'm talking to an audience of very experienced cosmologists, likely, but I always like to start from a little bit from the big picture, just to remind ourselves what are the big questions we're trying to answer. So this is my super schematic view of the expansion of the universe. Well, one of the, as I'm sure you all know, one of the most puzzling things about the expansion history of our universe is that roughly we can say 5 billion years ago, this expansion started accelerating. We attribute this to dark energy, but we are pretty much clueless about what this dark energy is. And despite this, we have like a model, lambda CDM, that is very simple, that it's built off GR. It depends on your 6 parameters, and these models seem to work very well in describing this expansion history. So it describes remarkably well the statistical property of the cosmic microwave background, but it also seems to work for all the subsequent evolution history of the universe. And this was for many years, I would say, confirmed by various different probes. Many years, let's say, until 2024, where things started getting more and more interesting. Even before kind of the 2024, let's say, changes, there were already some cracks, let's say, in the lambda CDM model. In particular, this model kind of fails a very basic test, which is predicting how fast the expansion of the universe is today, this H0 tension. And supernovae play a very important role in measuring H0, but today I'm not gonna talk about that. I'm mainly gonna focus on how supernovae can help us constraining if lambda CDM is the right description of our universe, and how we can pin down more and more what dark energy is. Anyway, after this brief introduction, so what we're trying to measure this expansion history of the universe, and what is the most direct way of doing that? Well, if you have a series of objects, astrophysical objects, astronomical objects for which you know the distance and the recession velocity, well, that's basically a direct tracing of this expansion history of the universe. And supernovae 1A serves precisely for this purpose. So supernovae 1A are these thermonuclear explosions of carbon-oxygen white dwarfs, and they are excellent distance indicators. So here I present like a beautiful, the most typical light curve of a supernova 1A that explodes, reaches peak brightness, and fades away. And the key point in supernova 1A cosmology is that this peak brightness, the intrinsic peak brightness of supernova 1A is very homogeneous, especially after several empirical corrections. So if we take the apparent brightness of a supernova, I don't know if you can see my pointer, apply a series of empirical connection that depends on what is the width of the supernova light curve, what is the color of the supernova light curve, we can infer very accurately the luminosity distance of the supernova and compare this to cosmology. So the luminosity distance basically encapsulate the cosmology and how the universe is expanding, and this is how you constrain how much dark energy there is, what is its equation of state, etc. So let's say if you forgot, if you didn't remember anything about supernova and cosmology, this is your very high-level summary. So the Dark Energy Survey specifically was designed to kind of combine some of the most powerful cosmological probes, including supernovae 1A, and try to measure this expansion history as accurately as possible. So for supernova science in particular, DES kind of drilled down these very tiny 3 square degrees fields and monitored these patches of the sky for roughly 5 years and found thousands of good supernovae 1A. And today I'm going to present you like what, after many years and a lot of people involved, as you can see in this picture, we use this supernovae to constrain the expansion of the universe. So to put that into context, I always like to start from comparing the DES sample with some of the supernova cosmological analysis, some of the most important cosmological analysis that have been published in the past 4 years. And I'm sure you have heard about both Pantheon Plus and Union 3, and I'm sure many of you have used those datasets in your analysis. So these Pantheon Plus and Union 3 are compilations. So they kind of put together data from many different surveys, 20 plus different surveys that have been conducted in the last 30 years of supernova cosmology since the field started. And both these compilations kind of combine these low redshift events. For us, low redshift is below redshift 4.1 and higher redshift supernovae. So between redshift 4.1 and 1. At high redshift, both these compilations were also using some DES data, like 200 roughly supernovae that we published 5 years ago as a very preliminary study. But I think what is very interesting to highlight here is that DES kind of revolutionized this picture, and with one single telescope, one single survey, okay, not 17, we kind of measured 1,600 new supernovae 1A, so new, never included in this previous analysis, that really pushed the redshift range much further. This is the blue histogram I'm showing here, okay? Now, DES, as Pantheon Plus and Union 3, also had to rely on external low redshift data. And here I present them in orange. And this is because at these very low redshift nearby distances, the DES camera was just saturating. Like we couldn't get access to these low redshift anchoring samples. So we had to use some historical supernova surveys. All of them were also included in Pantheon Plus in Union 3. The reason why, so with DES, we try to be conservative on which low redshift sample we included. And we try to include the most recent, the highest quality ones, and reject some of the kind of pre-2010 events that both Pantheon Plus and Union 3 try to include, mainly because, at least for Pantheon Plus, the goal was to do a measurement of both like dark energy, but also H0. And for H0, you need to go a low redshift. This was not something we were interested in doing for DES. That was not the point of DES. So we kind of tried to reject some of the lower redshift, less older kind of samples. Now, this kind of sample translates into this distance redshift diagram. We call this the Hubble diagram. And one thing I want to highlight here is one of the reasons why DES could go so much deeper in redshift and could compile such a large sample with just one single telescope is because we, differently from some of the surveys that were included in Pantheon Plus and Union 3, we kind of selected our events in a slightly different way. So while the surveys in Pantheon Plus like really spent lots of time trying to spectroscopically confirm that each event was a supernova 1A, this is something that takes a lot of telescope time, that limits your depth a lot. In DES, we didn't do that. What we did is measure the redshift spectroscopically from the host galaxy. So the x-axis is still spectroscopically measured. But what we did is we selected all supernovae for which the shape of the light curve looks like a 1A, regardless of whether we have an external spectroscopic confirmation of whether that event was effectively a supernova 1A or not. This clearly leaves some room for contamination that I highlighted here from events that look like 1As, but they actually have intrinsic brightness, but they're actually likely core collapse or other type of supernovae that have an intrinsic brightness that is not standardized. So they look like outliers in our typical Hubble diagram. One of the tools that we use to identify likely 1As just from the light curve has been machine learning classifiers, and I will talk a lot about that in a few slides. Now, so this is our sample, and I get this at the stage of how the DES sample look like and why it's different from Pantheon Plus Union 3, why it's deeper, why it's larger, but why it's also more contaminated, quote unquote. Now, I want to spend the next bit of the talk kind of talking about two important aspects. One is the various sources of systematics that DES was affected from. So as you probably all know, supernova cosmology needs to deal with quite a lot of systematics. And of course, this was the case for DES supernovae as well. So I wanna focus on that a lot. First, starting from this problem I just mentioned, that in DES we had the problem of contamination from non-1A supernovae, and we addressed this. Then I will kind of focus on how we deal with sample selection effects, which is another big systematic in supernova cosmological measurements. And then overall, I want to discuss about kind of how these systematics increased our cosmological constraints in DESS. And then I will present you the results, and we can look at the cosmological results. Before diving into the systematics, you have to bear with me for a couple of slides, and we will have to talk about simulations. Because, and I think this will become clear throughout the talk, in studying systematics, it was extremely crucial for an analysis like this to have good and reliable simulations of the DES sample. So I'll just briefly touch upon that in the next couple of slides. So when you talk to a cosmologist and say the word simulations, I know that it can mean a lot of things. So I want to just clarify, I'm not talking about n-body simulations of the universe. It's not that kind of simulations. Here, we're literally trying to resimulate the supernova light curves, the actual data. So we start from the astrophysical ingredients. Okay, we assume a cosmology in our universe, and we start from simulating supernovae exploding, both supernovae 1A, but also all the other types of supernovae collapse that we know contaminate our sample. And second, we kind of associate each of these supernovae to host galaxies. We know that supernovae are not randomly and equally distributed across galaxies, but we know that there is a very specific rate of different supernovae 1A or core collapse as a function of galaxy types, and these galaxies we know have a certain evolution across redshifts, have different dust properties. So we kind of try to map all these. But then on the top of these kind of perfectly simulated supernovae and galaxies, we apply all the observational noise that come from our telescope. And in particular, we apply all the selection effects that our imperfect survey is going to introduce in our sample. And I remind you, here we kind of have two observational effects. One coming from the DES survey, they measure all the light curves, but also all the kind of selection effect introduced by the auxiliary spectroscopic surveys that we had to rely on to get the redshifts, the x-axis on our Hubble diagram. Now, this second stage of characterizing the efficiency of our survey has been done super accurately for DESS, because DESS, throughout the 5 years of operations, monitor very well each night, like which supernovae DESS should have observed and which should have missed, given the conditions, the condition of the telescope, the condition of the atmospheric conditions, etc. Like, we really monitored the efficiency of DESS very accurately, probably most accurate, like the like nobody and no other survey has done before. So building the simulations was really a monumental effort of putting together all our astrophysical knowledge of these transients and everything we know about the survey DESS, and resimulate kind of the real sample, but with the advantage of kind of knowing the intrinsic cosmology. So here I'm just going to show very briefly a couple of plots that show how well we could reproduce the properties of our real sample. So here I have the distribution of redshifts, Host galaxy brightness, and the Hubble residuals, so residuals in Hubble distances, in distances. And these are the distributions we observe for the real data. Like, this is how our real data are distributed. And the ultimate test to check that our simulations are kind of accurate is to compare the real distributions with the distributions coming from your simulations, your simulated supernovae. And we really managed to kind of get an agreement between data and simulations that was excellent. And I want to highlight, it's not like here we're trying to fine-tune everything until we match what we want, but we really started from quote-unquote first principles. Like, we know the astrophysics, what it should do. We know what the DES survey efficiency was. So unless there is some big unknown in our assumptions, these two things should match, and they did match quite well. So this really gave us the confidence that we understand our data, we understand our selections, and we can use the simulations to do a lot of validation of our cosmological analysis. So the first thing we used these simulations for was train and test how well we can identify the supernovae 1A using just machine learning. So we used very different algorithms developed by a completely independent team. We set up like challenges, providing different simulations for which the labels and kind of the true answer was unknown. And we really tried to break these machine learning codes, trying to see if they were really giving the purity and efficiency that is required for high precision cosmology. And despite many attempts, and I have to say, when I started my PhD and I started working on these things, we were really starting from a very skeptical position of saying, these things are never going to work, so let's demonstrate that. And we kind of have to admit that it's quite the opposite. And these machine learning algorithms can do extremely well, also thanks to the fact that DES has very nice light curves in multiple bands. We tried to understand if this kind of purity and efficiency and amazing accuracy, 99%, blah, 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 were really enough for cosmology, and kind of run various tests, again, on both simulated data and real data. And here I show an example. Like, one of the many different tests we ran is, of course, comparing the kind of cosmological contours you get from a perfect simulation that has no contamination, only purely supernovae 1A, and the kind of contours you would obtain if you add inject this contamination and analyze everything using simply machine learning classification. And you can see immediately by eye that whatever shift this contamination introduces is much smaller compared to statistical uncertainty. And now you can kind of quote unquote do the same test in the data. Of course, in the data, you don't have the perfect data, but again, we try to reanalyze the data with different classification algorithms, different training methods, changing all the possible kind of variables in the parameter space. And again, the contours shift by an amount that is very small compared to the statistical uncertainties. And here I'll show how we propagate this to our final cosmological contours. Anyway, so contamination, let's say it's a not subdominant systematic that needed to be quantified, but wasn't our kind of main concern. The other important systematic I mentioned I would have touched upon is related to selection biases. So going back to my very schematic version of the distance redshift Hubble diagram, the problem that every supernova survey have and will have to face is selection biases. So the fact that as you go at higher redshift, you start missing the faintest and faintest supernovae. Okay, so here the kind of side of supernovae that you're going to start not seeing are on the faintest side. Okay. So this, of course, can bias the kind of inferred cosmological parameters and requires to be corrected. So both in Pantheon Plus and DES Supernova 5-year analysis, we quantify how efficient our survey is in recovering all supernovae, especially at higher redshift. We quantify these using simulations, the simulations I've been just talking about. And we use the same simulations to kind of predict which kind of corrections needs to be applied to compensate for this loss of supernovae. And in one of the papers that we published for DESS, we really focus a lot on how this kind of correction for selection biases has been measured and modeled. Clearly, one of the caveats in this process is that when you build your simulations, you need to make some assumptions on what is the scatter of these data points, what is the peak intrinsic peak brightness intrinsic variation of supernovae 1A. And part of studying systematics is if we change these assumptions, like how much our cosmology changed. That is something that we spent months kind of investigating, and we're still investigating. And this is also something that we had to include in our systematic error budget, let's say. These corrections, in fact, as I show in this plot, especially the higher redshift, where again, when selection effects become predominant, can be quite large at the level of 0.1 magnitudes. In DES, we kind of had two, in certain fields, we could go much deeper than in other fields. We have this two-tier approach. So we have deep fields and shallow fields. So you can see that in some fields, this effect was much smaller. In some other fields, this effect was more predominant. So we had to deal with this quite in detail and on a field-by-field basis. Yeah. Then I unfortunately don't have time, but there are at least 6-7 other papers I should talk about when I give an overview about systematics. Here I just put a brief list, so you're all invited to look up at all these other references. We looked at calibration. So in supernova cosmology, you always need to be very careful about your photometry being well calibrated. So again, we use a very similar approach to Pantheon Plus and calibrated both DES and all those low redshift supernova data we combined DES2 with. We try to improve how the light curves are modeled, and we have a whole set of systematics related to that. We looked into what fraction of supernovae might have been misassociated to the wrong host and so have the wrong redshift, and how this could impact our measurement. These are all a series of things that have been studied both on the data and on the simulations, and their impact on cosmology has been quantified. And this brings us to this kind of to discuss what is the role, how much these systematics uncertainties can affect our cosmological uncertainties. And here I show just for a flat WCDM kind of fit, if the statistical uncertainty on W is around 0.13. That was the result we got for DESS. If we add systematic uncertainties, we see that these are around 50% of the statistical uncertainty we started with. And we tried to kind of quantify which systematics affect our final constraint the most. And well, to give a very rough ranking, well, this systematics related to contamination from non-1A supernovae, which is one of the things I was mentioning a few slides ago, is actually what turned out to be one of the smallest systematics, even though at the beginning was one of the scariest one, let's say. While, for example, uncertainties in how we model this peak intrinsic brightness of supernovae 1A and how this impacts our corrections for selection effects. This is probably our top systematics, and I think is the thing supernova cosmology should focus the most in the next years. Okay, having said that, I'll go to the actual results, which I'm sure you've seen, but here I'm just gonna kind of summarize for a series of models the kind of cosmological constraints we obtain. And here, as a comparison, I'll always kind of present how the model compare to our best fit flat WCDM and compare with the data. So you can see which kind of variations we're trying to catch here. And you see that it's a game of few tens of millimax. So for flat lambda CDM, again, here I'm going to show with the DES supernova alone counters and DES combined. At the time, we combined this with Planck CMB measurements with the EBOS BAO data, which were kind of the latest BAO measurements we had at the time, and the DES 3x2 point correlation Wilhelmsen measurement from DES 3-year analysis. One of the first, slight surprises, I think I would be, I can say that, was that DES alone prefer a slightly higher omega matter in line with what Pantheon Plus already showed, I think, higher omega matter than CMB and BAO. So the DES supernova value alone is around 0.35. I guess at the time we didn't call this attention, but still it's interesting to see that things start to kind of push not at a 3 sigma level, but start to be discrepant on these like very simple flat lambda CDM, the simplest model we could start from. Adding degrees of freedom to flat lambda CDM, well, at that time, and I think that's has been an interesting evolution to see. At that time, our main focus, we were only caring about W. W is W minus 1. I found it very interesting that in the past year, probably, nobody cares about W anymore. Everybody wants to see W, not WA. And DESI even didn't present their flat lambda CDM results. Yeah, I guess this was back then our main main plot, and what we could see from a simple kind of flat WCDM model is that W is still consistent with -1 within 2 sigma. But I guess things become, well, we had to learn that things become very interesting when you really open up the parameter space, because W is still a very rigid parameterization of Dark energy, and you look at W not WA CDM fit. So what we could find again with DES alone is that, well, our constraining power, and we knew that, is not amazing from DES supernovae alone, but we could still see, and we could find still a 2 sigmas compatibility with lambda CDM. Things started to become a little bit interesting if we were combining while combining with CMB, BAO, and 3x2. But I guess our deviations from lambda CDM were still around the 2 sigmas, so we didn't emphasize, for sure we didn't emphasize in our results these as a groundbreaking result. But as you all know, things changed a few months later. Well, first of all, I'm gonna kind of be a bit DES-centric and advertised that. So in roughly a month ago, we kind of combined the DES BAO results and DES supernova results. So kind of the two DES geometrical probes combined together. We just published the results because BAO and supernovae kind of separately came out together last year, but we only recently kind of published the combined analysis. And what we found is that actually these, with the most updated BAO results from DESS, this tension with lambda CDM started growing above the 3 sigma. And I'm sure in the 19th of March, you all saw that DESI kind of also published similar constraints and found evidences that are breaking the kind of 4 sigma barrier, let's say. And here I present the very latest results. DESI plus CMB alone provided an evidence against lambda CDM of 3 sigma. One of the most interesting things is that I guess Pantheon Plus, Union 3 and DESS 5 year increase these evidence, at least in the case of Union 3 and DESS 5 year. And famously or unfamously, DESS 5 year became the supernova sample that pushes things the farthest from lambda CDM. Now, I hope that since this result came out and since DESI started presenting results on all these different supernova samples, I thought about always including kind of in my presentations of DESS some kind of overview of, we have these 3 samples and nobody quite knows what to use, which one to use, and there is always some confirmation bias. Like, I guess if you like lambda CDM, you tend to use Pantheon Plus. If you don't, you tend to use DESS 5 year. I hope in this talk I can also kind of clarify what are the similarities and difference between all these 3 samples. And I hope one thing that came across is that DESS 5 year is a photometric supernova sample. So we had to rely on machine learning to identify 1As, while Pantheon Plus and Union 3 both use spectroscopically confirmed supernova samples. So no machine learning involved, nothing. But another thing I want to highlight is that, as I mentioned before, Pantheon Plus and DESS 5 year use both this simulation-based framework to quantify selection effects and do corrections for these selection effects, while Union 3 use a completely different method to do that, and is much more based on this unity framework that is a Bayesian hierarchical method that is truly independent to what Pantheon Plus and DESS 5 year are using. So this is just to emphasize that there are substantial similarities and substantial differences between these 3 samples that are kind of summarized in this 2x2 table. The main difference between kind of Pantheon Plus and Union 3 and DESS 5 year is the data they're using. There's a little overlap, while Pantheon Plus and Union 3 are basically using the same data. But on the contrary, Pantheon Plus and DESS 5 year share almost the same methods for the cosmological analysis, while Union 3 is using something completely different. So I think it's still very interesting to see that these numbers kind of these contours all line this portion of the parameter space, despite the substantial differences that we know underlie these 3 different measurements. Now, very briefly, I think I have to mention that of course, the differences between these numbers, 2.8, 4.2, 3.8 sigma, kind of raise some questions. And in particular, I think in end of 2024, a paper by George Staffiu came out comparing DESS 5 year and Pantheon Plus. And here I'm kind of, for reference, I'm presenting, again, the residuals from a Planck-like cosmology for both Pantheon Plus in blue and DES in green. These two analyses, as I said, have a lot of substantial differences, I guess, in the data and not in the analysis. But one thing I want to emphasize here is that, so while Pantheon Plus has a much wider redshift range, as you can see, especially in the low redshift, it goes much low redshift. It also included some Hubble Space Telescope high redshift, very high redshift supernovae. Is the constraining power of Pantheon Plus and DESS 5 year within the same kind of redshift range is significantly different. In particular, DES, as it has more data, is much more constraining. So this is just to say that the two Hubble diagrams compared, I think provide kind of are overall compatible within the redshift range where they overlap, but they give slightly kind of different cosmological constraints on the flat W0 WA parameter space. Now, in these analyses that George proposed, George did something more than just comparing the two Hubble diagrams, but compared the subsample of overlapping events between DES and Pantheon Plus, which are roughly a couple of hundreds between the two analyses. And notice some puzzling discrepancies that kind of allude to the fact that maybe there is some systematics that is causing DES to provide such a bigger evidence of lambda CDM. Now, I think I'm not going to spend the rest of the talk on this. I'm just going to highlight that in January, we kind of put out a paper trying to investigate in details, like why discrepancies, what do they do to, and what does this mean for DES and Pantheon Plus? Are these two analyses really incompatible, or are they just, is this difference mainly due to the fact that they use different constraining power on different redshift ranges? I think very, very briefly, I'll summarize that in this investigation that I invite you to read in details. We highlight that kind of half of the discrepancy George highlighted in his paper are coming from the fact that we did some corrections in DESS 5 year that were not present in Pantheon Plus, but we also showed that if reversed these corrections, they still don't take away any of the evolving dark energy evidence that has been highlighted by DESI. And kind of the other 50% of the discrepancies that George highlighted is coming from the fact that just comparing overlapping events between the two analyses can be misleading because of how these two subsamples, these two data sets were analyzed. Again, this would require a much more detailed discussion, and I invite you to read the papers because I think it's much clearer than what I can say now in just a few minutes. So let me spend the last 5 minutes, I still have 5 minutes, right? Just talking about like, where do we go next? Is this the end of lambda CDM? Well, very personally, I think there's still a lot. Well, I would be very skeptical in saying that this is the end of lambda CDM. We have demonstrated that lambda CDM is not correct. And I think that there is still a lot of work that can be done. On the very short term, I would like to highlight some of the analyses that, at least on the supernova side, we're working on. The first one might be interesting for most, is this new kind of Supernova Unite compilation. So we have these three analyses. Why not combining all the data, in particular combining the data coming from DES and Pantheon Plus? And given we not only have these different data sets, but we also have these different methods in analyzing the data set, the idea is to kind of work together with the union team and analyze them both the DES way, but also the union unity way, and see like what differences or similar results we can achieve. So this hopefully is going to come out in the short term. I'm going to say this year, but you never know. But the idea is that all the data is there, all the machinery is there. The two teams are working closely together, and so this shouldn't require years to come. We're also kind of updating a few things in the DESS analysis. In particular, the points that we know are the weakest. So the calibration last year, after our results were published, we know that new kind of white dwarf standard star data for calibration of supernova data came out, and we're trying to update to see how much these new measurements would change our cosmological results. And then we are kind of proposing different modelings of these intrinsic supernova brightness variations to try to see if, again, if our systematics uncertainty associated with this modeling assumptions are correct or not. But in the long run, actually, the next 10 years are going to be extremely interesting, because there is a lot of data that are going to come out, especially on the supernova side. And in particular here, I want to kind of highlight 3 main surveys and how they're going to contribute to future supernova cosmological measurements. The first one is the ZTF and ATLAS surveys. They're both low redshift supernova surveys, so they will help us anchoring the Hubble diagram at redshift 0.1 and below. So a completely different range compared to DES 5-year, but a range where we only have historical data. We only have data that are at least 10 years old. So, so here there is a lot of work to do. Both ZTF and ATLAS are going to have thousands of supernovae. So we're going to effectively get a factor of 10 improvement on the lower side of the Hubble diagram. And this is going to be, I think, extremely important. And hopefully, again, these surveys are still running, but they have been collecting data for more than 5 years each. So these cosmological results should come out in the next couple of years at most. And this is the first, I think, milestone we should be looking forward to. But second, of course, we have LSST that is starting next year. I'm sure many of you are somewhat involved in that. And the amazing thing about LSST is that it's going to be basically, it's going to do what DES did for 5 years, but on an area that is basically 600 times larger. So the amount of supernova 1A data we're going to get is just mind-blowing. And in particular, well, here in the UK, we are leading a program that is going to run on Foremost, on the multi-object spectrograph Foremost, in order to try to get all the spectroscopic redshifts that are needed to do supernova cosmology with LSST. Now, I think I had a couple of slides just highlighting some of the things related to LSST, but I think I prefer to leave enough time for questions afterwards, so I'll skip that. The last kind of survey I want to mention very quickly is the Roman Space Telescope, which should be launched in 2027, plus or minus a couple of years, given all that is happening in the US right now. But Roman is gonna kind of contribute to future supernova cosmological measurements going at significantly higher redshift than we have ever done before. So if Rubin and DESS were kind of stopping around redshift 1, Roman is going to give us roughly 10,000 supernovae 1A, pushing the limits to redshift 3, which is something that supernova 1A never explored. And this is going to kind of extend our Hubble diagram on the high redshift side, far behind what we have been able to do in the past 20 years of supernova cosmology. So I think all these like series of surveys in the next 10 years are going to really enhance what we can constrain, how we can constrain the cosmological, the expansion history of the universe from the very low to the very high redshift range. And I think I'm going to stop here and take any questions.
Thank you so much. Very great talk. Do you have any questions? Satya?
Hi, thank you. That's really a wonderful talk, a great summary. I was wondering whether there is anything known about how supernovae evolve as a function of redshift, because the metallicity environment in which they live, everything changes. Is there anything known, and would that be more difficult or less difficult to model? Can you shed some light on it? I have one more point to make, but
Yeah. Well, you bring up a parameter of metallicity that is one of the nastiest ones. So we definitely see that supernova and intrinsic brightness have some dependence on the mass of the host, and we correct for that. Now, we know that the mass of the host, the stellar mass of a host galaxy, is one of the easiest parameters to measure with optical and near-infrared galaxy data. But it might be that that's just this dependency on supernova brightness with host mass is just the result of a much more kind of astrophysically motivated dependence. For example, metallicity. Metallicity is something that I'm sure you know is much more difficult to observe, to estimate if you have just photometric data. So I guess my answer is in 2 points. First, it could be that there is a metallicity dependency. For what our data are telling us, this dependency, if like this dependency is not going to be at the level of the cosmological kind of the cosmological effect we're seeing, because otherwise this would show up in kind of the scatter, the intrinsic, well, the scatter in supernovae 1A that we are observing.
yeah.
So the effect to really kind of wipe out WNOWA, CDM, or wipe out dark energy, this effect should be humongous, and we don't see this in the data. Yeah.
And the second
But
point,
I think, yeah,
sorry,
one of the goals, yeah, one of the goals of in LSSD, and in particular the TIDES program that is going to do spectroscopic observation of the host galaxies, is to try to answer these more in detail, like and constrain spectroscopically the metallicity of these galaxies. So the hope is that we will have a better understanding of what's happening in that. Yeah.
excellent. Thank you. I wanted to also understand how how important it is to fill the gap around redshift of 0.1. Adam clarified why you don't have many galaxies there. From a gravitational wave perspective, we don't seem to have much problem getting events. And when we reach good sensitivity, we might be able to get a couple of data points in that region over the next 3 to 5 years. And I was wondering if that's going to have any impact in the analysis. Probably not, but just wanted to understand.
Yeah, no, this is an excellent point. So just to clarify, the reason why there is a gap here is not because in the universe there is a lack of supernovae at redshift 0.1, but it's just because of how these surveys were designed.
No, that's right. Adam explained.
Yeah. So historically, supernova surveys, they were either going for very wide area, very shallow, and stay at low redshift, or like DESS, drill down a very tiny patch of the sky, but go as deep as you can. And this was because back then we were trying to constrain, like, is there dark energy in the universe or not? So you want a data point at low redshift and a data point at high redshift and compare the two. Now that the attention is moving to WNOWA and you need to trace all the wiggles, I think we will have to be more uniform and try to get as many data points. I mean, ideally, of course, you want as many data across all redshifts, low, high, and middle. That's always the dream. But I think with LSST, for example, this gap is going to be filled pretty easily because LSST, I mean, we'll find thousands of supernovae in this gap and then hundreds of thousands up here. But in a sense, like we will have a much better constraining power across the board.
Thanks, Maria. Wonderful. Thanks a lot.
Good.
Thank you. Niels?
Thanks, Maria, for the excellent talk. I was wondering, so given that a lot of these rising tensions that we're seeing are related to the value of the matter fraction in the universe, I was wondering if you could tell a little bit more about which kind of systematics are most related to this kind of curvature that you have in the Hubble diagram. So, for example, in the slide on the sample selection, you already showed that if you lose supernova in the high redshift end, that this could kind of act almost as such a curvature. Can you say a little bit more about what are the biggest systematics?
So you're asking, if I understand correctly, you're asking what are the biggest systematics that are gonna kind of be degenerate with having more mass or less mass in a flat lambda CDM?
Yes, exactly.
But also,
Okay. Well, I think probably like in a flat lambda CDM, which is the less rigid model, the things that well, I think that the two things, first suspects I would point to are on one side, calibration, because, you know, calibration, it means that you need to make sure that your telescope like is well calibrated and you could convert a digital signal to a physical flux of the supernova, okay? And each telescope needs to do that independently and internally. And DES did that very well because it was a cosmological survey that was designed to do that very well. Other low redshift surveys did that probably with techniques that were 10 years old. So in a sense, like we're trying to do our best in kind of retrieving those data, recalibrating them using the same kind of current techniques. But it's not like we have a time machine and we can go back and take better data and monitor the telescope kind of filters, throughput. And so in a sense, that's something that hopefully like the newest supernova surveys are paying a lot of attention to in order to kind of make sure that's not a problem. The other thing that you mentioned, actually selection effects are a bit nasty because they introduce kind of like they can introduce all sorts of like deviations of the Hubble diagram, okay? So mocking exactly what a different omega matter would look like is not as easy. But again, at the low redshift, because these surveys are 10 years old, it's back then there was a lot of like human decision involved in do we follow up that supernova or don't, which is something that in DESS didn't happen at all. Like everything was automated, no human decision involved. So is there a nasty selection effect in those low redshift samples that we're not aware about just because, again, we don't have a time machine, and that exactly mocks these different omega matter? This is a question. I mean, this is an open question, and I wouldn't bet my house on the fact that. No.
So what's the timescale on which we can expect like the newer surveys to give us the first like competitive constraints on omega m that are competitive with what we currently have?
Yes.
So in timescale, what I think, I'm not going to make any promise, but what I think is going to happen is SN Unite, so that's 5 year probability plus will come up. But that's going to rely on the low redshift surveys that we've been using. I'm personally very involved in Atlas as a new low redshift sample, and that I think is going to come out hopefully by the end of 2026, depending on how hard PhD students and postdoc work and us. For ZTF, I'm not as involved in the ZTF, so I would I'm not as sure. But I think, I mean, everybody is very eager to put out these low redshift samples before or as LSST starts, because that's going to be very important for me as well. So yeah.
Thanks a lot. That was super nice talk. Thanks for answering those questions.
Thank you. Sayantan?
Yeah, thank you, ma'am. Very nice talk, actually. So I was just having a question from a theoretical point of view. I mostly work on like phantom, like dark energies and and string motivated one, the Dirac Born-Infeld. So you mentioned that, I mean, this supernova samples shows that omega is like, say, minus 0.09, like, I mean, like greater than -1 instead of less than -1. So I'm just asking that, okay, I mean, of course, one can have something like quintessence one to falsify it, but with the latest string paradigm, again, I'm not defending anyone. I'm just asking that in the latest string paradigm, mostly people after swampland usually bet on the phantom one. So I'm just asking that how certain is the data strength? Like, do you feel like, I mean, when the systematics error are taken into, I mean, omega would still has a possibility of going less than -1, or like, is it something like it is converging to, say, greater than -1? So I just want to have that. Yeah.
Sorry, maybe I misunderstood the question, because so in all my results I always assume flatness.
No, it is flat. I'm just asking that the nature of dark energy. So if you want to take from a string paradigm, the swampland, etc., they prefer the phantom one, like less than -1 rather than 1. So I'm just asking that how pivotal it is to greater than -1. So I'm asking that in string paradigms, most of the models, let's say brain, entry-brain, like Neil Turok model, etc., they always get omega to be less than -1. Say, I mean, it is like a phantom type. Here we are getting -0.9. So I'm just asking that with the latest systematics taken into account, etc., sigma, do you think that omega could change, or you are like, I mean, you can more or less see that it is converging to greater than -1 itself? I mean, there is no hope of going to beyond -1. So yeah, that's what I
sorry,
get.
when you say omega greater or -1, you mean W? Okay. I think.
Sorry.
Omega
Omega is small
sorry.
omega. Yeah. Sorry. Small
I
omega.
totally understand.
Sorry.
I always get
Sure.
confused. I also get confused.
Yeah.
I was
Sorry.
just trying to. Well, I think I'm honestly not sure how to answer this question. I think
Yeah, my question is roughly like, what are the chances that with the future observation we can get omega, W less than -1? Yeah, so roughly like that.
Well, I mean, what are the chances? I think, yeah, I'm not sure how to answer this question. I'm sorry. I mean, the data could still tell us, especially if I think about the supernova data, like they're still kind of compatible with both options. It depends, of course, the CMB constraint, if they stay what they are right now, they're more sensitive to more negative values of W. I'm not sure exactly. I'm not sure how to answer this question. I don't know where these countries are going to move.
Sure.
Yeah.
And maybe just a small doubt, like, I mean, when you are taking a large range of redshift, I mean, to calibrate, etc., when you are taking, say, MCMC or any type of least square one, the range in the x-axis, that the redshift changes would literally leverage the, I mean, least square, right? I mean, when we do the least square fitting, we typically have Z, HZ, and delta HZ, and with some covariance, etc. So I'm saying that when you, statistically, so when you do the least square, I mean, the susceptibility of Z is not that serious. So if you are taking a long range of Z, it could, I mean, when you run, say, MCMC or least square, I mean, it could leverage the potential very much. Like, I mean, that's the reason mostly people focus on a particular Z range, right? I mean, so I'm just asking that, is it just a statistical problem, or it has been taken care of? I mean, let people typically avoid a large range of Z, at least as I have seen. I have not seen much, because there is a leveraging problem when you do the chi-square or other minimization.
No, I think the widest redshift range, the better it is. So yeah, especially for measurements like W and W not WA. So I think nobody's been trying to avoid, but actually quite the opposite. Like,
I see.
Yeah, I guess the problem is that the WCDM is kind of rigid enough that the wider redshift range, the more difficult it is to get away from the -1.
Oh, okay. Yeah. That's what I was wondering. That, I
Yeah.
mean, a small error in X could leverage your, say, analysis very much rather than your Y. Because delta Y you have already taken care in the least square, I mean, in your MCMC code or any Bayesian one. So
Yeah.
delta X could pose a problem. Okay.
Okay.
Thank you, ma'am. Very nice talk.
Good.
Thank you. Dan?
Hey, Maria. Really nice.
Dan.
How are you?
Very well.
I feel like there's been a lot of kind of constructive work on understanding the difference now between Pantheon Plus and DESS, where it's like half is due to different selection of the same supernovae, and then the other half is just some improvement in modeling. You show, though, that there's a third sample, Union, which is kind of right in the middle. And I'm curious what kind of these types of analysis, what is possible to be done with Union? Because a lot of these differences that people are pointing out between Pantheon Plus and DESS are things that Union would not be so sensitive to. It's a very different way. So
Yeah.
go ahead.
Well, because as you know, because Union, the Union analysis was done in a completely different way, is also not easy to make a one-to-one comparison. Because even like very simply, but Union 3 didn't release a proper kind of Hubble diagram, distance versus redshift, just because in their framework, this is not necessarily an output. I think, well, I think it's extremely interesting that Union sits right in between Pantheon Plus and Union 3. So I think I don't know if I'm answering your question, but I think one of the things we're trying to work on now is reanalyze DESS 5-year, both simulations and data, and as I mentioned, DESS 5-year Pantheon Plus combined with this Union framework to see like to kind of cross-validate these two methods. But yeah, as I said to all the people that asked me to comment about these three numbers, is you can be unhappy with Pantheon Plus and DESS 5-year, but still Union remain the elephant in the room because it's completely different people, it's completely different way of analyzing the data, and yet you get a pretty large evidence against lambda CDM. So I think what we're doing now is with this data, okay, that has been used across these three different analyses, kind of fill this gap in this quadrant. Like, let's analyze the DESS 5-year data with the unity methods, and kind of trying to combine and cross-analyze data sets. I think that's the main thing we can do now. Yeah, I don't know if this answers your questions or add any.
It kind of does, but I'm also asking, can other people do this? Like, is it possible that, I mean, we've had these good constructive analyses with trying to compare Union 3 and the others?
Well, can other people, I think, well, for sure on the DESS side, there has been a lot of effort in making everything available. On the Union 3, like, people can grab the codes on GitHub as far as I know, and could kind of do similar comparisons to the ones that has been done between Pantheon Plus and DESS 5-year, even though it's a bit trickier with Union 3. So
Thanks.
yeah, sorry.
Thank you. George?
Yeah, could I just make a comment on how to test supernova systematics? I think that you don't need a big sample. What you need is a well-controlled sample. So you don't need to to have the huge redshift reach. Okay, if one can get a nice well-controlled sample that spans the range sort of 0.02 to say 0.3, something like that, that will be good enough, I think, to tell you whether there, the sort of systematics that I was worried about of some sort of transition mismatch is playing a role in any of this. So the thing that worries me with DESS 5 Ia is it's a very big sample, but the photometry is not that brilliant. I mean, the magnitude errors are big, and we want to get this match down to 0.01 mag. So so looking at more carefully controlled higher quality photometric sample, where the photometry is a lot better, I think is the way to test this. So if they can sort out ZTF photometry, maybe, and match it with a good high quality intermediate redshift sample, maybe that will do it.
Yeah, well, I think
But go
ZTF.
for quality, not volume, is basically what I'm arguing.
Yeah, I think this is a very valid point. I mean, ZTF is not going to give us a sample that is as deep as redshift 4.3.
No, that's right.
So ZTF is always going to rely on high redshift surveys. I'm surprised by your comment that the photometry for DESS is not great, because I think DES made a pretty good job in calibrating the photometry and like sampling the light curves. So I'm much more concerned about the photometry for some low redshift samples. And or some other surveys. Like, I mean, ZTF itself is not a cosmological survey, so they will have to work. They are working pretty hard on making their photometry good enough, because calibration was not one of their priorities.
All I meant about that, Maria, was that when you look at the residuals on the Hubble diagram, you can see that the spread is very big, right, for DESS 5 Ia.
Well, when excluding the contamination, because I agree.
Yes, but even when you exclude the, you put a high cut in for the non-type 1As.
Yeah.
Well,
I think he was fairly like compatible with other high redshift supernova surveys. So when I say let me add just one comment on this. When you say we don't need higher statistics, we need better control sample, I totally agree. In a sense, higher statistics, which is what LSST is going to give us, is going to help us to get a better control sample, in the sense that one of the things I'm looking forward to do with LSST is, do things like, since we're going to have hundreds of thousands of supernovae 1A, we will be able to select maybe only supernovae 1A that have the bluest colors. We know those are the less affected by dust extinction, or supernovae in only very specific host dust environments, host galaxy environments, because we know that when you start doing that, you obtain very small, much smaller scattering Hubble diagram.
Like selecting blue supernovae, for example.
Exactly. Like when you in experiments like this, you can be picky in a sense. You need to take all supernovae across different environments, across different ranges of supernova color and supernova stretch. Well, when you start having hundreds of thousands, you can start to be picky and say, I want only the subsamples of supernovae that I know are the golden standard candles that have very low intrinsic scatter. So in that sense, I think statistics is going to help, because it's going to allow us to do that in a way that has not been possible before, because before it would have been just a statistics killer for any analysis. So in that sense, I think something like LSST is going to be very interesting. Not because in a sense, making supernova cosmology with 1 million supernovae, I agree, we're going to be systematic dominated. That's not the point. The point is, among those 1 million, we can really select the best, the golden sample of very homogeneous standard candles, and that's what we're aiming to. Yeah.
We can thank Maria again.